The following production is sponsored by the National Science Foundation's Network for Earthquake Engineering Simulation program. The effects of these combined behaviors are investigated by a series of experimental tests performed at the University of Illinois. 5 small-scale bridge piers were subjected to the individual and combined effects of shear and torsional loading. Fabrication methods, testing procedures, and test results will be presented. Earthquakes pose one of the greatest threats to mankind due to their potential to devastate communities, regions, and even entire countries. Earthquakes rank second in the cause of human fatalities by natural disasters, surpassed only by floods.
The challenges that earthquakes pose to us in terms of their effect on infrastructure and on society are quite wide-reaching. Earthquakes affect everything. In terms of networks, transportation, utilities, structures, education of the population that is displaced and hence deprived from access to schools, economy, loss of the tax base. The effects are very wide-reaching.
Shear stress is a stress which is applied along the surface or plane of a structure. When applied to a square, it causes it to take on the shape of a rhombus. Shear stress is applied to a bridge pier when there is a lateral movement of the top of the pier relative to the bottom of the pier, which is fixed in this case. The effect of this deformation creates tensile stresses that tend to crack concrete, which is much weaker in tension than in compression. Shear stresses act along a line that is typically inclined at approximately 45 degrees to the longitudinal axis of the pier. Torsion is a twisting action about the longitudinal axis of a member. Since one end is twisted while the other is held fixed, shear cracking and stresses are created in the member due to torsion. By examining a small section of this member, it's easy to see the shear forces acting. If you recall the diagram of the stresses from an applied shear load, they look very much the same as these stresses produced by torsion. When a member is subjected to a combination of shear and torsional loads, the stresses due to shear and torsion will be additive on one face, while counteracting each other on the opposite face. It is expected that the first crack will appear on the side of the specimen where stresses are additive. Cracks will initially travel diagonally along that face. The nature of their propagation will depend primarily on 2 factors: the type of behavior, shear or torsion, which controls the individual test case, and the reinforcement provided. In this test, the specimen was subjected to a 1-to-1 ratio of lateral displacement and rotation, as explained in the loading protocol, in order to induce both shear and torsion stress. The general behavior of cracking for combined loading specimens can be explained by the fact that the lateral movement also induced bending forces. Tension and compression zones developed on the faces adjacent to the side of the specimen where cracking initiates. The cracks then spread along the adjacent tension face horizontally until it reaches the other face where it would still experience compression due to bending. The compressive zone will finally arrest the crack. It should be noted that for the 1-to-1 case of combining lateral displacements and rotations, the ultimate cracking pattern shows shear cracks in the same direction on both the front and back of the specimen. This indicates that the shear behavior dominates over the torsional shear in this loading case. This is further supported by the observation that this level of additional torsion did not significantly reduce the lateral shear capacity of the specimen. In contrast, the presence of lateral displacement severely reduced the torsional strength that the pier was capable of producing when compared to those reached in the pure torsion test. This test involved a highly brittle failure, which is shown by a very sharp drop in load-carrying capacity of the specimen, and was accompanied by the rupturing of several strands of transverse reinforcement. Therefore, it is important in the design of columns that support bridge structures to make accurate assessments of the magnitude of the shear and torsion that may be imposed during an earthquake, as well as to fully account for how the capacity of one is reduced by the application of the other. It is necessary to design for these considerations in order to improve the safety of buildings, strength and reliability of bridges, and enable our infrastructure to perform better in natural disasters.